And Joseph, did I record you? Yes, you're permitted to one. I think I did yours already. Yes. Okay, you're welcome. You're welcome. That's good. That's good. And let's try one more. Okay. All right. I think we're good to start out. And okay. 1 second while I scan my handwritten notes. What are we going to do today? We're going to do about half. We may go for a long time today, but I hope that in the future weeks, starting next week, I hope to have 1 hour, 50 minutes of lecture on concepts and architecture, and then 50 minutes of open discussion on programming. I'll look at shared programs. I'll try to debug them for you. We'll work on programming. But right now, what I'm privately trying to do is bring all 3 of my assembly sections to the same starting gate. So we're all equally spaced. And my fault was that during the first 3 weeks of the semester, I let some things slip, but we're going to make them all parallel now. All right, so I think I left off with, maybe I did it, or it was the last thing I did, was to make sure inputted numbers were valid, namely positive. If I did this in the last class meeting, let's just bear with it for three to 5 minutes, and we'll do it one more time. This is an example of, well, you know what? I got to make the announcements. Johnson is waiting for you at 5:30. Would like to see you. See you at 5:15 is actually it. For SI discussions. Okay. So I think he's going to focus on what I do in lecture. That's what his supervisor tells the SI instructors to do, is to emphasize and reinforce what the main instructor does in the main lecture. Okay, I'll look up his Zoom number later. I don't have it right at hand. And one more announcement was, I'm going to remind you next week. Next week on February 22. 22, there's a job fair in person. It's not Zoom. Titan Student Union, and it starts at 3 p.m. Oh, that's right in the middle of our class time. But it goes to 6 p.m. Okay. I'll remind you again next week we meet in class on the 22nd. The job fair is good for everybody, even those not looking for a job. If you're not looking for a job, you should still go over there and just learn what they do, learn what is happening. Go to each one of those tables, pick up any literature they have about the companies, save it, because those are your contacts in the future when you're actually seriously applying for a job. Look at how other people are dressed. When you see some classmate of yours wearing a brand new suit with a tie, he's seriously going after a job. He's going to get one of those job recruiters to hire him right there. And what do the ladies wear? You have to look like a businesswoman or like a business lawyer. That's all I know about it. Ladies, you have to find your own wardrobe for that, because I'm not very good at that. But for the guys, you better have a nice tie. If you're not looking for a job, you're just surveying the scene, then you can go in student clothes, and that's okay. All right, that's the end of the announcements. Let's, where's my first page of, where's my first page? Okay. Oh yeah, we were going to find an example. Let's do it. Example of validating an input. In particular, in the first program, there were two sides of a triangle that are not allowed to be negative. So we have a, we better set it all up. Okay, so let's say that XMM 15 is side 1, XMM 14 is side 2, XMM 13 is side angle in degrees, and XMM, somewhere in the past, we converted that to angle radians, RAD, and XMM 11 is sine of XMM 12, and XMM 10 is 0, which is 0.0. All right, and we want to check to see, is side 1 positive? Okay. I'm going to run it. That sheet of paper is not going to hold the answer. Okay, if I've done this before, you just play along, and then we're going to move on. Okay, so we write assembly in blocks, and each block has a sentence to describe it. Validate side 1 XMM 15. Okay, so it would be, I didn't explain 0. Let me do the solution. And I got to come back and explain about 0. So U, ISD. Occasionally I should look up to see the messages, no messages. And let's, either order will work. XMM 10, XMM 15. This is 0. This is side 1. Okay, so if, where's the bad case? XMM 10 is greater than XMM 15, but we don't say greater when we're working with float numbers, we say above. So that's the bad case. Jump above JA to negative input, negative side. That sounds better. Okay. And so negative side, I mark it someplace far away. Negative side with a colon. Okay. If it's not, if above, if this is false, it's not higher than that one, then it's going to execute normal processing here. So continue, this is comment territory, continue, validate side 2. And compute the area. All right. If it is above, the 0 is higher than the length of the side, then we're down here and it will execute this one. And this is where you give the user a message, invalid input, output message. Try again. Run the program again. And then we go to, I'm going to make a comment, set return value do all the pops and RET. Okay, we have a control execution control problem here. When this executes, we don't want to then immediately execute the thing that says you have bad inputs, try again. So we need to bypass that with a JMP to someplace further away. I'll stick it in here, exit. And you can't see it, but it's hard to see. EXIT with a colon. Okay, that's the general outline of an if-else statement. If this is true, it executes this part. True. And if this comparison back here is false, then it executes this part. And this is the false part, where is testing to see if the first number is larger than the second became false, they execute this area. It is an if-else statement like other languages have, but it's not as pretty. It's kind of ugly the way it's organized, but you do your best with that. Okay. All right. So we got past. Oh yeah, I was going to say something about 0. Okay, we took care of validating an input, but now here's a side message. Why do we use assembly? Why program in assembly? There's one strong answer and there's one secondary answer. Program in. Okay. So I'll give you the strong answer because it's faster than any other programming language. Faster. It executes faster. That's number one. And secondarily is it can interact with parts of the hardware that other languages can't. Access to hardware. I mean, right down to the machine metal is what we're talking about, to hardware. That other languages can't. They have to interface with an API layer in between or talk to the operating system first and get permission. They don't get direct access to the hardware that assembly does. So I want to focus on this one. What is fast and what is slow? If an instruction executes entirely inside of the CPU, it's going to be pretty fast. As opposed to, I'll tell you, if the instruction is outside the CPU. In the processor. It is fast. In its execution time can be measured. There are experts who go around measuring every instruction to see how long it takes, and it measures in 3 to 10 nanoseconds. That's very common for one instruction to complete its work. It moves the data into the ALU unit, carries out the operation, assigns the result to a register. If an instruction goes outside the processor, a common average execution time is 3 to 10 microseconds. Okay. That's a factor of 1,000 to 1 slower. The machine can do 1,000 of these in the processor instructions in the time it does one of these out here. Well, what's an outside the processor? Well, pop RAX. It has to go out to memory to get some number and move it into RAX. That's an instruction outside. What's an instruction inside? Add RBX R14. See, that never goes outside the microprocessor itself. That's entirely inside, and that's a fast instruction. Okay, so what does that lead up to? It leads up to a technique of putting 0 in a register. Okay, here it comes. In some other class, you probably learned what XOR does. XOR looks like this leads to something. Okay, you have true, false, true, false. True or true is true. True or false is this right? False, false, true. I can't explain it, but I'm pretty sure I got it right because I looked it up this morning. Okay, in computing, that's math class. In computing, we'd use zeros and ones. Okay, so it'd be 0, 1, 0, 1. Oh, I see why it looks so weird over there. The true is actually a 1, and the false is actually the 0. Now I have the 2 columns flipped over. It's okay. 0, 1, 0. Those of you recording it, this is not important. This one is important for us. That's how XOR acts on bits. The 0 bit XORed with the 0 bit is 0. The XOR bit with the 0 with the 1 is a 1. And you can figure it out there. Okay, so if you have 2 registers, XOR RBX, R10, it takes 1 bit from here, 1 bit from here, and performs the XOR and leaves the answer here. This is the destination. The old data in RBX is lost. Okay, so I can't write out 64 bits, but let's just pretend there are only 4. Is 1, 0, 1, 0. And R10 is 0, 1, 1, 0. Okay. So what will XOR RBX R10 look like? So you start either side. You take these 2 together and check them on the table. Right now it's a 1 and a 0. The table says 1 and a 0 is a 1. I can't get this table in place here. Is there that? I think that shows up. Okay. What did I say? We have a 1 first and a 0. The answer is a 1. Okay, so 1. The next is 0 and 1. That's a 0 and 1 is 1. Next is 1 and 1. 1 and 1 is this 0 down here. And the last one is 0, 0. That's a 0 here. There's our answer. That's the new value in RBX. Okay. There's a meaning for this. What happens when you perform an XOR on itself? RCX, RCX. Now it gets dicey. RCX, I have to make up something. Let's say it's 1001. And so RCX is the same thing. 1001. And what is the new answer after XOR? RCX. RCX. Well, you form an XOR on these two ones. 2 1s is a 0, where I'm pointing here. And then you perform an XOR on these 2 zeros. 2 zeros is a 0. And then it repeats itself. Another 2 zeros. And then a 1 and a 0. I did. No, I miscopied that. This RCX is supposed to be the same. 1001, 1001. Okay, 2 1s, the XOR is a 0. What did I get out of it? I got a 0. Okay, so what is the conclusion here? XOR is a way to put 0 in a register. Now, why am I even showing you this? The reason is it's fast. Here's the instruction right here. It never goes outside the register to do its work. It does it all inside of the ALU, inside the arithmetic logic unit. That's going to be really fast. When you need speed in your program, like decrypting a strange document or something, you're going to try 100 trillion combinations. You want the whole program to run fast. Okay, so now one more step. We're going to apply that to XMM registers. Where do we have it someplace? Right here. XMM10 is supposed to have a 0 in there. How can you get a 0 in there? I know the slow way, but how do you get a 0 in there the fast way? Here it is. XOR. Okay. XOR by its 3 letters only applies to general purpose registers. To apply it to XMM registers, we have to attach this. XMM10, comma, XMM10. And if you look at it, just by eyesight, you can see there's no converting some other thing. It's all done inside of the SSE component, which is inside of the processor itself. It never goes outside to do this operation. The end result is that XMM10 will have zeros. I'm going to write zeros. when it's done. Okay. All right, that was a sidetrack. How did we get there? We got there because we were comparing zero against a good value, a hopefully good value. And you need to have a zero sometimes in your XMM registers. This is, now you know how the experts do it. Let's see the question. Okay, we're going to go on. Okay, in that assignment number 1, it then says compute the area. I think this is kind of a trivial answer. I promised last time I'd walk all the way through it. Let's walk through this answer right now. Okay, so it's a block of code, and it says compute area of given triangle. Okay, so let's do it. Move SD. Number 9 seems to be not in use. XMM 9, comma, side 1. Multiply XMM 9 by side 2. Multiply XMM 9 by XM, the sine of the angle, XMM 11. And we're done. Oh, is it? Oh, gee, is there a divide by 2? I think I missed that one. I think the form, if you know the math better than me, maybe you can correct me, but I think the formula is the area of the triangle is side 1 times side 2 times the angle between them, sine of the angle, the whole thing divided by 2. Very technically by that. We don't have the 2 here. We need one though. Div SD XMM 9, register number 8. 8. Okay. Oh, I gotta put that on the list. Oh my gosh. XMM 8 is 2.0. Okay, we got to pause here and find out how do you get 2.0 into a register. We know how to get a 0 there. 2.0, I think the only choice is we have to use the convert instruction. Okay, so it goes like this. Move, pick any register. RAX is a good workhorse. And then CVT SI to SD. Where's it going? It's going into number 8. XMM 8, comma, RAX. That's all. It's a 2-line operation here. Okay, so this this long instruction name converts the number 2 here, and it reformats it. All the bits shift around to a different form and puts a 2.0 over here. And we're going to learn about all that bit shifting in the coming days. Okay, it's an intensive operation. There's no shortcuts like XORing zeros or something. It does a lot of work, but there's no other way. So I would not expect this to execute in 6 nanoseconds, more likely 30 nanoseconds, because of the extra work it's doing. Okay, what happens next? We're almost at, I'm going to jump to the end. The next step is to output the area with annotations. Okay, so let's do this, and then we're going to switch subjects soon after that. Let me look up. There's no question. Everybody, maybe there is. I should look and see. You need to have a value in X first, or can we just use, oh, you don't need a long, you don't need a value in there in first. You can just go directly to it. What is the value of X before operating XMM9? Oh, I put the initial value in there. Right here, it had some junk in there, unknown information. And I put a copy of side 1 in there. And then I multiplied side 2 times the side 1, and it became a new number. Then I multiplied by the sine of the angle, and it became another number in there. And then I divided by 2, and it became the final number, which is the area. I'm using XMM9 as a destination place, so I can work on it by this side number, this angle value, this sine value, and then this division by 2. If I don't use XMM9, I'm going to lose one of the sides. Suppose I started working on it with XMM15. I think you see the issue. If I don't put a copy over here, you can go straight ahead with it, multiply SD XMM15 times side number 2. Okay, now you have the product of the two sides, but you lost the value of the first side. And you could multiply this by the sine of the angle. It's okay. You could divide that answer by the 2.0, and it's okay, but you've lost the value of the first side. Maybe you don't need it anymore. It's okay. But if you needed that for later use, this is not the way to go at it. Okay. Let's see. What is the value for? We move side 1 into it. Yes, he answered it for you. Okay, good. I see. Okay, you got it. Okay, I want to make it. I won't do these many times in the future, but you need to see formatting for output. Future assignments, I assume that you can format your output. We have to go back. We're going to output a message that says the area of the triangle with side this and this side and this angle is something. So it's a long sentence. Okay, so this is area message. DB. The area of triangle now. Let's pretend you're at the side of your text editor. You don't have more space. So you close off the quote marks and you come over here, usually directly under DB, but it doesn't have to be. Put a new DB, which is a continuation of the same message. The area of the triangle with side 1% 116 LF and quote, we ran out of space, so we continue over here. The assembler will treat it as one long string. with and side 2. .16 LF and got too many hands, and dB angle percent 1.10 LF is, okay, we'll still go on, dB percent 1.6, I'll tell you why I pick on 16 in a moment. 16 square units, SQ units, backslash 0 quote 0. Okay, that goes back in the data segment. And it shows I'm going to output 4 numbers in this one command. There's a number for side 1. There's a number for side 2. There's an angle number here. And then there's finally the area that was computed. Okay. Can we handle all that? I think so. Why 16? Okay. LF is the symbol for formatting data of type double. C++ has type double. This is for data numbers of 64 bits. Floating point. The precision of 64-bit float numbers is somewhere between, it actually varies whether you start with the digit 9 or you start with the digit 1, but that's not very important. It's somewhere around 17 to 18 decimal digits. So if I ask for 16, I'm pretty sure that all 16 are significant. They're not electronic noise. If I tried to output 20 digits, like %1 20 LF, you only have assurance that probably the first 16 or maybe the first 17 are numerically correct. The extra digits on the end are just going to be electronic noise. They don't represent anything. So 1.16 is pretty good. If you want to print 20 digits, use 1.20, and you'll see all 20 digits, but the 3 or 4 on the right side are going to be meaningless. What does the 1 mean? 1 right here means always show at least 1 digit on the left side of the dot. So if I'm outputting a number that happens to be like 0.75, it will always show 1 digit on the left side, and so it'll come out as 0.75, and then there's 20. You got all this stuff after it. It works okay. What if the number you're trying to output is 375.66, but you only have it formatted for 1? Well, the answer is the machine disregards your 1 and it goes ahead and uses 3 anyway. So you still get the whole number, even if you put only 1 there and you have a 3-digit in the whole number position to be printed, to be outputted. All right. Okay. Anybody okay? Let's finish this story. Okay, I'm getting ready to output this big mess. Here it starts, and it'll continue on the next page. Print F. Sorry, everybody. You got to do better. I'm jumping ahead. I shouldn't do that. Okay, four float numbers. That's what you tell RAX. It says, be prepared. I'm going to send 4 float numbers to printf. Okay, the first float number is coming. XMM0. And that's supposed to be side 1. So I go back in my notes and I find side 1 is XMM15. XMM15. Okay, the next number is side 2. Move SD XMM1. What is side 2? There it is. It's number 14. XMM14. What's the third number? It's the angle. Oh, okay. The angle is 13. Move SD XMM2 XMM13. What's the fourth number? The fourth number is the area that we computed. What did that come out to be? Where was it? I think it was number 9. We did all these calculations, and when we divided by 2, we got a number 9. Okay, so move SD XMM3 XMM9. Okay, now printf, like all the other functions in the whole world that have floating point parameters, they look for them in this consecutive order. There's no jumping around. If it has a single floating point parameter, it will always be found by the called function in here. If the function you're calling has 3 float numbers that you're passing to it, it will find them in here, here, and here in that order, in the parameter list. And our example uses 4 float numbers, so it goes up to XMM3. Now, just as a side note, you can't go beyond number 7. If you had to fill up, that's 8 floats you're passing. If you're passing float through 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7, you've reached the limit of the registers, because the machine does not look at registers above number 7, like number 8, 9, 10, up to 15. Okay, but we're safe here. This is all good. All right, so then we call printf. Yeah. Printf is programmed correctly. It goes up here and says, I gotta find the first 4 float numbers. So it picks up the first float, the second float, the third float, the fourth float, and places them in that sentence that's back here. First, second, third, and fourth number outputs a nice, beautiful sentence, and your supervisor at work is very impressed. I just added that. Okay, you know how to do it now. There's the working example. All right, we're going to end the program. So let's say that you say goodbye. Move to, you know what, I missed, folks, I missed one. We got to go back and fix it. No, we're okay, but we need to insert one little line. The name of this is called the area message. It's supposed to be right here. Move RDI area message. The rest is good, but printf needs to know what the formatting is. The formatting is all included inside of this area message. Okay. So printf goes and looks at the area message, knows that it has to find 4 float numbers, picks them out in order from 0 through 3, and it's set to go. And now you get your nice output. All right, into the block. Now we're ready to leave this function. We want to return to the caller. Let's look up. So it shows at least 1 on the left. Greg, you said it right. That's right. Okay, so the instructions say return the area back to the calling function. The calling function written in C or C++ language. The answer is it always is returned through number 0. Okay, so we have to say move. I missed the SD. Let's try. Move SD XMM0, comma. Who stores the area? I think it's number 9. XMM9. So a copy of the area is sitting in XMM0. And now we go into the block, restore the registers. General purpose registers. I'm not going to write all this, but you know. And then you say return. Okay. This has no effect on that. It's still holding XMM0, still holding the area. When the return happens, that will still hold the area, and your driver program got started by a statement that was like this. And let's put it in a color that's different. The driver has this in it, double area, and then down here it says area equals triangle parentheses, and this executes, and then all these things we're talking about happens, and here at the last minute the area is placed in XMM0. C++ knows that it has to fill this one from XMM0. And it does. And area has its number, and you can output it from C++, and you'll get the same answer that you got by from assembly. We did all this work back here. We got it there from assembly, but C++ will get a copy of that number through XMM0 and will display it for you. Okay, so here's a rule. If a function, any function, returns a float, 32-bit or 64-bit, doesn't matter, it will be found in XMM0. C++ does that. C++ function number 1 calls function number 2. Function number 2 computes a float number and returns it. It will be in XMM0. Okay. If a function returns an integer, long integer, short integer, whatever, ASCII integer, doesn't matter. It will be in RAX. Okay. Only those two registers return values to the function that called the function. Okay. Okay, let's see. Any questions? So this is only if the driver. Oh. Or Greg, that's a tough question. Okay, I have to answer that because that's important. In the world of all computing languages, we have two classifications. We can classify them in two ways: the compiled languages and the interpreted languages. Okay. So compiled languages give you a complete executable file at the end of compiling and linking. You get an exe that you can pick up that one file and run it in another computer. That's C++ does that, and C language does it, and assembly does it. Okay. On this side, those languages compile halfway to sometimes to a file called bytecode. And then you can only transfer it to another computer where the runtime system is already built to understand that. I'm very familiar with Java. A Java file, you have to have a name. Assignment1.java compiles into an intermediate file that's not executable. And you can name it anything you like. Stuff. I forgot, I think it's called out. But you don't even have to use their customary extension. You can use anything. Then you have to feed that into an interpreter box, which is more software. And then that outputs executing statements that actually execute one by one. So you get some output from running the program this way. Languages on this side don't link with each other. They're very specialized. They have to have their own specialized interpreter. The interpreter for Java can't interpret the C# instructions. Okay. On this side, these languages link together. Fortran has a small niche in the world. It's not very common, but it links with all these others. See, if it's a fully compiled language, we can link them together and they all act the same. They all transfer data back to a caller through this one register. And if they're returning an integer, they all use the same register. On this side, it's not the same. You don't have. One thing is you can't mix languages here. You can't have Java call a function written in Python or vice versa. They all stick together. You write the entire program in Java, and then it's not even an executable. Once you compile it and remove the error messages, you have a halfway compiled file, which you let an interpreter take charge of and try to instruction by instruction execute it. So it's a completely different style. Over here on the compiled side, what you asked, Greg, is true. You can do parameter passing among languages that are fully compilable. That's the deciding question. Or are they interpreted languages? I was once going to introduce a little bit of Fortran in this class, but we have so many other things to do. It's not worth the time. Just to show you that a fully compilable language is linkable into all your other source files. I guess I'm going to leave it there at that. Okay. Uh, we're just we're gonna work on these three here as a working example. If you end up at some corporation where they have an unknown brand new language and it's compilable, look around, you'll probably find other languages mixed in. But if it's if you're at your company and they use Java, Python, and C#, you build the whole thing in one language because it has to go through the Java interpreter or the C# interpreter in order to execute itself. Okay, let's see, anything else? Why do we use driver file to return stuff but not? Oh. Yeah, okay, that's, I'll tell you more about that. All the assignments this semester will have at their top level, usually a C++ starting block, or it could be C block. They're so close together, either one could do it. And this one will have a statement that calls an outside function. And I draw it with an arrow. That outside function could be another C++, but in most cases it's an assembly. Okay. That's called hybrid programming. It's a mixture, hybrid, it's a mixture of assembly and other functions. And when you call printf, you're actually going outside of, you go out here and you connect with another function made by somebody else, but that doesn't matter. Or you connect with scanf and made by somebody else. And we don't know what language they use, but we don't really care. It all connects together by a linker. The best I've read about is most of these are written in ordinary C. Most operating systems, like the Windows kernel and the Linux kernel, they're written in C language. Okay. But when you're going to call printf, all you have to do is put the extern statement in here, and it's all connected. The linker knows, the compiler, the assembler knows, hey, there's a function on the outside that I'll deal with later. And same thing with scanf. This is called hybrid programming, where you have mixed languages in the same system. Now, the opposite side is called pure assembly. Okay, and I'll make another diagram. You use nothing except assembly. The introductory block is ASM, and this is driver, or I like to call it the introduction. And it calls another assembly, ASM, and this is managing the problem, called manager. And then it calls something else written only in assembly. You can't mix other languages. This is get data into the array. And then it calls another function. This is written in assembly. And this is compute the sum of the array. Okay, this is really pure. No mixture of anything else. Pure assembly. So Greg was asking, does this have to be C++? No, it doesn't have to be, but this is hard. When you do it 100% in assembly, that means you're not allowed to call printf to output your information. Printf. You're not allowed to call scanf to get your numbers in. You're not allowed to call, what's an outside function that we might want? Sine, we did this sine of an angle. You can't call functions from a library that belongs to C language or to C++ for that matter. If you're writing all assembly, that means you have to program this stuff yourself in assembly. And it is very, very tedious and time consuming. And I don't think it's a good teaching tool, is my opinion. Later this semester, I'll show you one example where you can have assembly everywhere if you like that. Especially even the first one. There's a way to set it up so that, and you can't link with G++. If you're doing pure assembly, you can't link with C language. These are out of the question. There is a linker called LD that's part of NASM, and it will do the linking for you if every function is assembly. But for teaching purposes, to learn the most possible that we can, the most we can in 15 weeks, this is not the way to go. This is a lot of tedious hard work. It's better that we have access to library functions like these and like these and like these. Okay. Yeah, exactly, Tuan. We're more flexible. We have access to outside functions that make our life much better than it would be if we didn't have access to those. There's a lot of professors in, if you go online, look at the famous universities, MIT back east, or Princeton University, or University of California and Berkeley. You'll find assembly classes that only teach pure assembly. Those students, I think you're still suffering. They suffer a whole lot more. But it's more flexible and more useful if we can call on library functions. And do the hybrid style. So that's what you're going to see the rest of the semester. You're going to see this style, hybrid style. Usually there'll be one or two modules that are in assembly, but there'll be other stuff that's not assembly, C and C++. We could make them Fortran, but it wastes time learning another language. We don't want to. We don't have enough time the way it is. Okay, any questions? How's our clock say? Our clock says 3 o'clock. I got to introduce you to concepts. Okay. I want to finish off chapter 2. At the end of chapter 2, there's a diagram of memory. I think I've done this before, but let's just pass through it one more time. Low addresses here, high addresses up here. And the author tells us, it's correct what he says. He says in the lowest block, chunk of memory, there's your operating system executing all the time. When you run a program, it will be placed as close to the operating system as the loader can put it. So this is your EXE code in here. Then the author is writing for assembly programmers, so he shows the assembly style. He says next to it will be the data you declared in .data section. You declare some strings, and they will be placed in a block of memory very close to your program that's executed. And even a little bit farther away are those that are in .bss. And then there's open space here. No. There's just open space here. and this is, depends on who you're reading, but this is the heap area. Some authors call this whole thing the heap. I don't know which is right, but it really doesn't matter much. At the other end, when this function here starts executing, a chunk of memory at the top end, at the high end, is set aside for the use by this program. Let me rephrase that. This program has a main function. A chunk of memory is set aside for that main function called an activation record. And online, you'll find a second name for it called a stack frame. It's the same thing, just a second name for the same concept. So this matches with a function that the executing program down here is currently executing. So on the side, I'm going to map it as function number 1 as part of the big program is executing. This function owns this chunk of memory, and it stores there the local variables that are declared in that function. They get stored in this area. A whole bunch of them. When function number 1 calls function number 2, still part of the same program, this is closed off and becomes dormant, and a new chunk of area is created, new AR, that belongs to this function. This function owns that area, and this function stores the values from its own variables in that area. If it declared a double, a W, and assigned to it 3.95, there'll be a place in here that stores 3.95. So all the variables in C++ that belong to this function, they have their values stored in that activation record. Anyways, this is memory organization, and you can see a picture of it on page 19, if near the end of chapter 2. And I'm going to conclude here by reminding you, this is where RSP is. It's the lowest address of the activation record currently executing. And RSP, change color, is the high address of that same activation record. I'm running out of ink there. Okay, I'll just stay with green. Okay. This is RBP. Okay. Sometimes I'm going to say, lots of people say, RSP is the front end of the current activation record. RBP is the back end of the current activation record. So they mark the front and the back. RSP is front, RBP is back. You can see the B in there, that is the back. The P is pointer. S is stack. Stack pointer is the front. Back pointer is the back end of the activation record, right there. Okay. Do we have denodes? You don't have you can use C and C++. You don't have to have deep knowledge to use it and mix it with assembly. No, and you've gone through a lot of semesters of C++. You have more than enough. You have knowledge about all those class structures. None of that exists in assembly. You just need basic knowledge of either of those two languages, and you'll do just fine in assembly programming, hybrid assembly programming. Okay. In future class meetings, I hope to turn the second hour into question and answer period, like debugging program. But right now, I want to get caught up with the Monday, Wednesday class, and we're almost there. Okay. No more questions. So chapter 3. Chapter 3 is about numbers. We're in concepts here. Okay. It introduces integers first, and then later in the chapter, it talks about floats. Integers. So to get familiar, we'll assume that we're in the old days. Our register has only 1 byte. One byte each register, which is 8 bits in each register. Okay, so an integer number will have eight bits: 0, 1, 0, 1, 1, 1, 1, 0. And by general agreement, this one is not the number. This 0 says positive. And a 1 will say the number is negative. So the number itself is the rest of it. Okay, here's how we figure out what that number is. Let me rewrite it over here. 1, 0, 1, 1, 1, 1, 0. Okay. Starting from this side, we count them 0, 1, 2, 3, 4, 5, 6. And then we agree that this is the value of 2 to the 0. The next one is 2 to the 1. Next one is 2 to the 2. 2 to the 3. 2 to the 4. 2 to the 5. And 2 to the 6. Okay. That's their place value. But in the number that you're looking at, the zeros are missing. They don't contribute anything. So it's in a sense that we cross him out, and we cross him out, and you add all the others. Okay, 2 to the 6 is a 64 plus 16 plus 8 plus 4 plus 2. And that looks like 80, 88, 92, 94. This number back here is 94. Okay. So what you're seeing here is an example taken from a system of numbers called 2's complement. Okay. And it can be applied to, like right now, 8 bits, or it could be applied to 16 bits, or it could be applied to 64 bits. 2's complement integers. And if you Google search for, if you web search for 2's complement, it will give you the rule. Here's the rule that it will show you: is to compute the negative of a number, negative of an integer, any integer. The way there's an algorithm here is you flip all the bits, including the sign one, the one on the outside. You flip all the bits to their opposite, then add 1. And the result will be the negative of the number you started with. Result equals negative. Okay, we're going to use that principle in about 2 minutes. And how are we going to use this? Okay, so Just keep it in mind. We're going to flip bits in a few minutes. Okay. First step, in an 8-bit system, 8-bit registers, first question is, what's the largest number? Just 2. What is largest integer? Okay, so we can figure this out. If it's going to be large, it just has to be a positive number. So the first bit has got to be a 0. Then there's 7 more choices. And you want to pick bits so that it comes out as large as possible. There's only one thing that makes sense. All ones. If the rest of the number are all ones, you can't get any larger because there's no 2's in this system. There's just 1's and 0's. That is the largest number. And this is it. This is it in base 2. Okay, what is it in base 10? Oh, we have to go back to the hard math. Remember, this one is 2 to the 0. This is 2 to the 1, 2 to the 2, all the way down here, 3, 4, 5, 6. The last one is 2 to the 6. And this one doesn't get included. We got to add them all together. So the answer is in 2 to the 6 plus 2 to the 5 plus 2 to the 4 plus 2, 3 plus 2, 2 plus 2, 1 plus 2, 0. Anybody know what that is? So I don't have to wear out my brain. Looks like.
Isn't that 127?
I think you're right. I would bet so. That's it. That's the largest number, largest integer. We're not talking float here. This is the largest float. This is the largest integer in an 8-bit register. If you took the time to add them all up, I'm sure you'll get 127. Largest int in a 8-bit register. Okay. Now, let's do the next. The hard one's coming. What's the smallest int? But let's do an intermediate difficulty. What is -1? Okay. Now, here's the hint. You have to think about that rule of flipping the bits. So we're after this guy. But we start with this one. And that one's pretty easy. That's the sign. And then there's +1. That's pretty easy. Now the rule we'll apply is flip all the bits. 1, 1, 1, 1, 1, 1, 1, 0. That's the flip. But then the second part of the rule says add 1. And then you have 1, 1, 1, 1, 1, 1, 1. And then the rule says that's negative of what you started with. There's our answer. Okay. -1 in decimal is equal to this one in binary. Okay. Got that. Now we have to solve the hard one. What is the smallest Let's see if I can get anything. What is smallest integer in this system? What is smallest? Int. Okay. We have to know how that works. So, I forgot how we go at this. Oh, well, one way is here is logical thinking. If it's smallest, it surely has to be negative. So start with a 1. And then you want all the bits after that to be as small as possible. That would imply all zeros. And I think it is. I think that's correct in binary. This is smallest integer, smallest. But it isn't, I don't have any feeling for, what is that, 110 million or something? I want to know what it is in real decimal. So this is the only thing, before class, this is the only thing I can think of. Let's like an algebra. Let x be equal to this one. And then we're going to add 1 to x. Let y equal x plus 1. And if I add 1 to this binary number above us, is 1, 0, 0, 0, 0, 0, 0, 1. We got a 1. Okay. Now, okay, now I want to know what this is, but my eyes tell me it's a negative number. I'm going to flip the bits and get the positive value for it. So we're starting here. Y equals 1, 0, 0, 0, 0, 0, 0, 1. So here's the flip. 0, 1, 1, 1, 1, 1, 1, 0. And then we add 1. Okay, so plus 1. 1, 1, 1, 1, 1, 1, 1, 0. And by the rule, the algorithm of 2's complement, this is now negative y. But we can figure this out. And in fact, I think we already did it. Here it is on green ink. See a 0 and 1's after it. That's what we have. 0 and 1's after it. And we determined that was 127. 10 minutes ago, we just did that problem. So this is positive 127. Got it? This is algebra. Negative y equals 127. It must be that positive y is negative 127. But if we go way back here, y is equal to x plus 1. More algebra. Remember, you plug in what you started back here. And this whole thing is negative 127. The question is, what is x? By algebra, you subtract 1 from both sides. X is negative 128. Okay. There we are. The top of the page says, let x be the smallest possible number we can write down in binary. And we determine that it is negative 128. That happens to be correct, actually. You can search online and that'll be the correct answer. Okay, so I want to summarize what we've discovered. Largest is plus 127. Sorry, it's supposed to be that's 127. Smallest negative 128. See if I have room here. This one was 0, 1, 1, 1, 1, 1, 1, 1. This one was 1, 0, 0, 0, 0, 0, 0, 0. Still with this? Okay. Those are correct. Then you flip back the pages or roll your tape back, and you'll see that's what we came up with. This is summarizing it. Okay. You know, we gotta play this game correctly. Here, I want to clean this up even more. Largest 127. And okay, let's group those bits in groups of 4 as that's customary. Okay. Now, as a number by itself, those 4 bits, they have a value. That's 2 to the 0, 2 to the 1, 2 to the 2. You add them together, 4 plus 2 plus 1 is 7. Okay, these have the same pattern. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. You add together 8 plus 4 plus 2 plus 1, it's 15. But we don't write 15 in base 16, we write F. So now here we go. 127 equals 0x7f. See how I got there? By writing out its bits of 127 and grouping them by 4s, you can decipher what each group of 4 represents. Those 4 is a 7. Those 4 make an F. And that is right. In fact, 127 really is 7F. Okay. Now, what about negative 128? That's 1, 0, 0, 0, 0, 0, 0. Same grouping, group of 4. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 4, 2 to the 3. 2 to the 3 is an 8. All these are zeroed out. They're just 0. So negative 128 equals 80. Okay. We're making progress. High and low. Oh, we left out negative 1. Negative 1 is 1, 1, 1, 1, 1, 1, 1, 1. It's in groups of 4. We did it just a minute ago. What are 4 1s? 4 1 is an F. So negative 1 is 2 Fs. Well, 1 F for each group. Okay. Okay, okay, you're still following this. Why did you add 1 before flip? No, I didn't. That would be wrong, Greg. I hope I did a 1 after flipping. Would you know the correct number you just flipped from 1? No, let's go back. Adding 1 is wrong. Adding 1 twice is wrong. Oh, I think you're referring to the algebra to get there. This is not applying the rule of 2's complement. This is, I want to work on, if you try to apply the algebra on here, I tried it earlier this morning. It was a horrible mess. But if you look at one number larger than that one and call it y, the algebra works nicely, sort of nicely. So I'm saying, let's let y be 1 larger than the number up here and see what happens. And here is that one number larger. Okay, so we're going to work on this one because your eyes tell you this is a negative number. Negatives are harder to work with than positive numbers. So now you flip, now we apply the algorithm. Here's why. You apply the algorithm. Flip first and add 1 second. And here's what we get from it, which can be easily computed to be 127. But the algorithm says what you're getting is the negative of what you started with. So this is negative y is equal to positive 127. Okay. Then you do algebra. You get y is, then you put the substitute, plug in the equation for x, and you get this line, and then you solve for x, and you get x is negative 128. And that's the solution we wanted way back here to know what that was. It's 128. Okay. Now this is just reformatting the answer in terms of hex digits rather than binary digits. And here's a summary. That largest number is this one. The smallest number is this one. And the minus 1 is this one. Okay, so, lost the lost the mood. Okay, so let's do that. We're working in the special case n is equal to 8 bits. And right in front of us, there are two numbers that are kind of important, largest and smallest. Now you got to think hard. How can I express 128 in terms of these 8? You have to, it goes like count by twos, count by powers of 2. Powers of 2 count 1, 2, 4, 8, 16, 32, 64, 128. Let's work on this one. 128 is really close. That's 2 to the 7. Smallest equals negative 128 equals negative 2 to the 7, which I'm going to write as n minus 1, because n is 8. But that number is really 2 to the 7. So we have this expression to match negative 128. Now, what about largest? Largest is 127. It's one number short of the one above. That's equal to 2 to the n minus 1 minus 1. See, I got it with, if I cover up the minus 1, then that says 128. But to get that answer, I have to subtract 1, and then I have this expression telling us what 127 is. Okay. You still with that? Okay, these play a role, because if you look at this all alone, it's not tied down specifically to 8 anymore. It could be that n is 16, or in the case we really want, it could be that 8 is 64. So in our registers, like RAX, n is now 64. The largest integer we have in 64 bits, I don't know what it is in decimal, but I can do it in exponential. it's 2 to the 63 minus 1. And the smallest one in exponential is up here, negative 2 to the 63. Okay, and that in fact is true. You can search online for binary numbers, 64 bits, and it will tell you stuff just exactly like that. These are formulas that are frequently applied. I mean, with 64, 32, 16, and 8. You could apply it to something in between, but nobody's interested in like n equals 20 or n equals 40. These are the interesting numbers because there's actual computers that actually use those sizes for their registers. Okay, let's see, we can. Are we done with integers? No, we're not quite, but we're close. Well, we shouldn't lose sight of in 64 bits. Yeah, we're almost done, everybody. Again, 64 bits. That's our n number. The largest one is a 0 followed by 63 ones. How can I write that without wearing your hand out? Wearing my hand out. It would be 0x. Okay, now it starts out 0, 1, 1, 1. That's a 7. And then there's all ones after that. I got 16 of these. 16 digits. In our registers that we're programming with, that's the largest integer with a sign that we have. Okay. And the smallest one, if you look back at it, it's it's just, here it is in 8 bits. It's an easy extension, 0x8 0 0 0 0 0 0 0 0 0. That's, I don't know what it is in decimal, but that's the smallest integer possible, and is very negative. Large magnitude, but very, very negative. And believe it or not, -1 is 0x. It's all F's. We saw that, I think, is it gone? In 8, oh, there it is, right in front of us. -1 in 8 bits is all ones, which interprets as many F, 2 Fs, one F for each group. But now we have 16 groups. Yeah. 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 Okay. There's our 3 big numbers that are kind of famous. The largest, the smallest, and the -1. Okay. Let's see. How's our time looking? I need to end in the next 3 or 4 minutes. In future class meetings, we're going to have the first hour only on concepts, and then I want to debate. I want to help you with your programs. If you have a bug in your program and it's the middle of the weekend, like Friday night, you should post it in Discord and get some help there. But if you can hold out until class time, I'll look at it during the second hour of our class meeting each day. You can share your screen with me, and I'll give you my best knowledge on how to remove bugs from your program. If you email it to me, it goes in a work queue, which is really slow. You'll probably get a faster answer by posting your question in the assembly Discord. Okay, so let's see if what we can do. Suppose we had, I want to go for 16, n equals 16. And we have a number, 0x 087 f b 0b 0. And we add to it 0x 07 d 5 8 5 8 a. Okay, can we add this stuff? Well, I don't know. Looks hard, doesn't it? Okay, I'm going to add this. I'm doing little Indian. I'm going this way. Let's start here. Least significant bytes are over here. 0 plus a is a. That's no big deal. B represents an 11, and you add 8 to it, you have decimal wise a 19. 19 is really a 13, isn't it? And you carry the 1. 1 and 0 and 5 add up to 6, nothing to carry. B plus 8 sounds like, hold on a second. Well, that's the same ones over here. So it's another 13. Carry 1. Okay. 1 plus f is equal to 10. Did I get that right? 10 plus 5 is 15. So you put a 5 here and carry 1. 1 and 7 is 8. 8 plus d is 21 decimal, which sounds like 15. Did I get that right? Somebody might be checking my math. I'll try it again. Okay. Okay, 1 plus 8, 1 plus 7 is 8. Now I have to add this d to 8. That sounds like decimal 21, which is 5 greater than 16, which means another 5 here, and we put 1 here. Okay. If I want to add the 1 and the 7, that gives me 8. So then it becomes 8 and 8. 8 and 8 is like decimal 16, but that's really 10. Okay, 1 plus 0 is 1. Okay, is that correct? Oh, we don't have, oh, that's too bad. This is a 16-bit calculator. We don't, my calculator in the terminal, in the window here is not 16 bits, it's 64 bits. I think it's right. Is there any way to be sure? Yeah, maybe so. Let's see if I can share the screen. We have to prove that this is. I'm gonna prove this. Internet graphics terminal. Where are you at? Okay. Share screen. Calculator. Okay. See over here. Change to hex, and then my first number was 087F. In calculations, don't put a blank space in there. Then it's B0B0. And then I click on the plus sign. And then what's my second number? 07 D 5 8 5 8 A. And press enter, or actually I'll press the equal sign here. And it says 1055-363A. What does the piece of paper say? That starts out 1055-363A. That's how you do arithmetic when you add. Okay. Everybody can do that? Is this really a piece of cake? Okay, what is B equal? B is equal to 11 in decimal. And then you count forward. C would be equal to 12 in decimal. Okay, everybody, we're out of time, but I hope you got something out of this. These are kind of fun things we do on midterm concept test, not midterm programming test, midterm concept test. Okay, so you're catching all these binary integers. Hey, it even gets better when we do binary float numbers. Oh, that's really a lot of fun. So, okay, so because we're out of time, I hope you have a very nice evening. And don't forget poor Johnson. He's over there waiting for someone to talk to him. Go talk to him at 5:15. And wish that he has a nice, happy weekend. He spends all day working on assembly stuff because he's so enamored with it. All right. Goodbye, everybody. Have a nice weekend. You're welcome. You're welcome, Nick, and everybody else, Joseph and Nick.